So this is an example problem from chapter 2, problem number 30. And the idea is that we have a flask or a bottle, maybe an Erlenmeyer flask, set up where we're going to heat the water inside and the air inside, often by boiling water, and then stopper it. And the idea is that you stopper it with an egg, and we get a pressure differential that kind of sucks the egg into the bottle. And so this is asking us to do a calculation for this, assuming an ideal gas. So let's look at the information that we have. We have a bottle with a volume of half a liter, so we have a volume of this of 500 milliliters, which I'm going to go ahead and take into cubic centimeters because I want to work this in our MKS units, and this is going to be different than what you usually see in chemistry. And so to convert that into meters, here's the trick. Almost all of these are unit conversion issues, as you might know if you've done this in chemistry. So if I want 1 meter and I want to change that to centimeters, notice I can't just divide by 100 and say that's 5 cubic meters because I've only gotten rid of 1 of the centimeters. So I need to cube this. And so when I do this, I get a 500, so this gives me 500 over 10 to the minus 6, that would be cubic meters, or I would write this as 5 times 10 to the minus 4 cubic meters, okay? So 500 milliliters is 5 times 10 to the minus 4 cubic meters. It says the temperature is raised to 80 C, okay? So we have a temperature of 80 degrees C, which we want to take into Kelvin if we're going to do anything with the ideal gas law. We've now moved into a region of thermodynamics where we really need to be in an absolute temperature scale. And the one that we use is Kelvin because we have all of our thermodynamic constants in terms of Kelvin. So if I do this, then that'll be 80 plus 273 to take it into Kelvin, which will be 353 Kelvin. Okay, so great, I've got information. Well, the pressure inside remains an atmosphere because the bottle is open. And part A is how many moles. Okay, so what's the number of moles? The pressure is 1 atmosphere, which is also in our units. We want this to be in newtons per square meter, so this will be 1.01 times 10 to the 5th pascals, where that's our unit of pressure. So Pascal is a newton per square meter. You may or may not remember that from Physics 1. So then it's just a matter of doing PV equals nRT. And if we've got pressure in pascals, which is newtons per square meter, volume in cubic meters, then when we multiply these two together, we'll be in Newton meters or joules. So we want to use our R in joules, so that's going to be 8.31 joules per mole Kelvin. And I know you may be used to seeing this in other units, but this is the units, this is the value that we'll use for if we stay in MKS units. Okay, it's all about the units for this stuff. Okay, so I'm just going to calculate how many moles are inside. So I've got pressure is 1.1 times 10 to the 5th newtons per meter squared. All of that times 5 times 10 to the minus 4 meters cubed is equal to the number of moles, which we were trying to find, times 8.31 joules per mole times Kelvin, and then times the temperature, 353 Kelvin. Notice what happens with our units here. This cancels with this. This goes there. Newton times meter is a joule. So all of that works out nicely. And so this becomes 50.5 is equal to N times 2933 per mole. So if we divide both sides by this 2,933, we get a number of moles that's equal to 0.017 moles. Okay, so that's how many moles of air is in this flask if we assume that is an ideal gas. Okay, that's part A. Part B, let's go back up here. Now we put the egg in place. Okay, so we have our temperature of 80, so we put the egg in place like this, sealing the bottle. And what's the pressure? So the new pressure, so part B, is what's the new pressure once the air has cooled down to 25 C. Okay, so for this setup for part B, what we're wanting to do is we say, well, the number of moles stays fixed. It's this value that we found. The volume also stays fixed. And so the temperature goes down, and from PV equals nRT, if the temperature goes down and these terms are fixed, R is a constant, so R is fixed, then the pressure must also go down. So we can actually, we don't have to calculate all of these things. We can just say pressure over temperature is equal to nR over V, and this is a constant. Right, that's sort of an easier way to work this instead of having to recalculate all these numbers again. So you can say the pressure 1, or pressure of part A over temperature of part A, is equal to pressure 2 over temperature of 2. Actually, I'll call those A, and this will be part B once things have cooled down. So pressure A is 1.01 times 10 to the 5th pascals. Temperature of A was 353 Kelvin, is equal to pressure at B, that's what we're asked for, and the temperature at B, the problem says, is 25 C, so 25 plus 273 gives me 298 Kelvin, 298 Kelvin. So my pressure B is 298 over 353 times an atmosphere. And so that gives me, when I calculate this, about an 8.5 times 10 to the 4th pascals, which is a fine number. We're not sure exactly what it means, so I'm actually going to do a little more than the problem asked for just to get a sense of what this actually means. And so, first of all, it's asking for, I think, what's the gauge pressure? Okay, so that's the pressure. What I'm interested in, though, is sort of how much force this egg is feeling. So if I look at this flask, ooh, that's lovely. And I know my pressure outside, so my pressure outside is 1.01 times 10 to the 5th newtons per square meter. And I know my pressure inside is 8.5 approximately times 10 to the 4th newtons per square meter. Then the question is, what's the force on this egg? How much force is pushing that in? And so what I want to know is, what is the difference in the pressure, right? Because that would be my force. So my delta P would be P on top minus P on the bottom, right? Because the bottom pressure pushes up, that's P on the bottom, and that's the pressure on the top pushing down. So this difference in pressure, if I subtract these two from each other, I get that that's about 1.6 times 10 to the 4th pascals. And then to find the force, I remember pressure is force over area, so this net force, this downward force, would be my net pressure times the area. And so I look up, actually, the radius of an Erlenmeyer flask, and I find that it's about 2 or so centimeters, 2.2 centimeters, for a I don't know which Erlenmeyer flask, but that seems about right for an egg to sit in. So if I write, that would give me an area, this open area right here, of pi times r squared, which, remember I need this in meters, so 0.022 meters. So that gives me an area when I calculate that, of about 1.5 times 10 to the minus 3 meters squared. When I put this in here and that in there, I get a force of around 20 or so. It's actually 24 newtons. So a pretty substantial force to act on this egg to push it down. Okay, so that's the first problem. The second problem we're going to look at is just, again, getting used to the units. This is, and to get used to sort of speeds of things. This is asking your VRMS for helium when it's only a degree above the point at which it liquefies. So it's just at 5 K. This is pretty cold helium, okay? The liquid helium that we keep in the double-walled jacket up in the NMR machine is, of course, below, is at 4 K or slightly below, but helium liquefies at 4 K. So the RMS speed we right, is just the square root of 3 Boltzmann's constant times the temperature times the mass. Now, Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. Our temperature is 5 Kelvin. And then again, we've got to watch our units. This mass, because we're in joules, which is newtons times meters, right? So that's that tells us that our mass needs to be in kilograms. So helium has a mass of 4 AMU, right? Just look it up on your periodic table. And an AMU is the mass of a proton, so I have to look that up. It's 1.67 times 10 to the minus 27 kilograms. So if I put all of these in, so my total mass is 4 times 1.67 times 10 to the minus 27 kilograms. So I've got something that's times 10 to the minus 27 down here, and something that's times 10 to the minus 23. So we know it's still going to be, you know, a reasonable size. This VRMS, when I put all of these in here, I get about 176 meters per second. So it's still going at a pretty good clip, even at 5 K. And you could, of course, say if I go 4 times fast, go at a temperature that's 4 times bigger, then because I've got this square root in here, in other words, 20 K, really warm, then square root of 4, then I would see that my RMS speed doubles, right? Because it's going as the square root. So that gives you sort of a sense of these numbers. They're pretty big, especially when we're looking at something as light as helium.